el llamado para el doctorado, no sé si te llegó. Yo le mandé un mensajito a Sebastián, a ver si se quiere juntar esta semana.
¿Pero con Seba o...?
Quiero ver si quiere charlar del trabajo de él, pero estaría bueno ver si...
está grabando.
Recording in progress. Okay. Sería bueno ver, charlar un poco el tema de...
No. ¿Cómo te presento? ¿Eres de Chile, de La Serena o...?
Sí, ya llevo 12 años.
¿Pero naciste ahí?
No, más al norte de Chile,
¿En dónde?
cerca de Antofagasta.
Cerca de Antofagasta. ¿Y luego dónde estudiaste el grado? ¿O
Las dos en la Universidad de La Serena.
Vale.
Licenciatura de...
Acá un mosaico chiquitito que tapa,
sí.
tapa un trozo de la izquierda. Y ahí ya te lo dejé. ¿Agua? ¿Te traigo agua?
Ya, por favor.
Buenas.
Sí, que hay un problema de suministro.
Sí, porque en teoría está pedido la garrafa de agua. Digo, no sé por qué no la trajeron. Yo pregunté la semana pasada y decía que ya lo tenían pedidas, pero que no la habían traído. Han elegido buena época para dejar sin suministro acuático.
Lyman-break.
Sí, se nota, ¿eh? El proyector que es nuevo.
Es verdad, yo digo, se ve
Qué
con
bien
mucha
se ve todo el
calidad.
color.
Digo, se ve con mucha calidad, no puede ser.
Sí, hay que pasar. Se notan los volúmenes.
Qué maravilla.
Se pueden resolver.
Se pueden resolver. Sí, acá. ¿Mirasteis la puerta?
Creo que estuvo viendo mantenimiento.
Vino alguien de mantenimiento. Ayer estaba suelta, se soltó como el marco donde engancha el casquillo de la puerta. De la de abajo, de la...
Sí.
Estaba ahí con
Se ve que
tornillo suelto.
desdoblaron un poco la chapa y lo volvieron.
Pero lo de la película no entiendo.
Pues está bien.
Es un follow-up de otros vampiros que aparentemente
En X de no tiene eso. Tiene una genes por la ancha o en X. Queda 24. Mucho. Entonces tiene masa día 8, día 9, algo así, ¿no?
10 a la 8, estoy leyendo.
Lo viste también, ¿no?
Os he escuchado y digo, a ver. Así que,
¿Qué número?
Lo curioso es que hoy salió el formato espectroscópico, no tiene ninguna línea de emisión.
pero siguen diciendo que es detección robusta. Yo lo estoy mirando ahora. O sea,
No, que es detección robusta en X. Sí, ese es el otro. Pero.
no tienen líneas, es verdad. Pero el break, con el break dicen que está claro.
Pero el break no te la genes, ¿no? O sea, el indicio de que es genes es porque
Así que Ricardo ya tiene que presentar los juegos.
Eso.
bueno, let's start. Okay. Thank you for being here for this extra seminar in summer. Normally in August we don't have seminars, but we have visitors. We do a phone. So today we have Ana León. She is finishing the master thesis in the University of La Serena. She's from close to Antofagasta and studied the degree and the master in La Serena. She's doing the master with Ricardo. She will be here this week. And today she's going to talk us about the kinematics and winds in analogs of Lyman-break galaxies. So, whenever you want, it's all yours.
Hi everyone, my name is Ana León. I am a recent graduate for the master in astronomy from Universidad La Serena. My project is titled the ionization gas kinematic and the stellar wind in the local analogs of the Lyman-break galaxy. And this work was supervised by Ricardo Marín and Vital Fernandez. Yeah. Maybe you wondering where is La Serena? La Serena is a city of the Chile. This is the map of this is Chile in the South America, and this is some picture for the La Serena. It's taken for me, and the particular privilege for this city is near the various observatories like Cerro Tololo, La Silla Observatory y Las Campanas Observatory. This is La Serena, and for example, Cerro Tololo maybe here, and La Silla here, and Las Campanas here. This is the outline of the presentation. So, the introduction, cosmological context, the organization era is the epoch occurring between the 15 to 6 redshift in this epoch. And it's very important because the first galaxy emergent, and now we can observe it with the advanced telescope like the WST. But the galaxy evolved until today. And this galaxy, we found the galaxy more normal, more larger, and with no present the extreme property like the Lyman-break galaxy or the high-redshift galaxy. But in focus of the project, it's the study the high-redshift galaxy, but using the local analogs to the galaxies. We have the Lyman-break galaxies. They are the high-redshift galaxy and selected because we are bright in the ultraviolet. And these galaxies are selected using the color criteria and specific the dropout technique. This technique is sensitive to the presence of the Lyman-break, this example, and superposed to the far ultraviolet continuum in a star-forming galaxy. And this technique uses the photometry. And the main property of this galaxy are the low mass. We have the high star formation rate, and they are luminous and compact in the ultraviolet. And this is the typical spectrum composite the ultraviolet for the Lyman-break galaxy using the survey boundaries. And you can see the Lyman alpha and another lines, the absorption and emission. Other properties important this galaxy is this galaxy are the low metallicity. You can see with this plot the mass metallicity relation for Henry 2021. And this is the sample for a stack the Lyman-break galaxy. It's showing the low metallicity. And another property important is this galaxy showing the complex kinematic profile for Yerena 2023. And this is the illustration. Yeah. This is the illustration. This is the baryonic cycles. And this is important between this process. For example, it's the aggregation gas, the recycled gas, and the ejection, like the outflow. The whole process is impacting in the evolution of the galaxy, and it's regulate the star forming and chemical composition and dynamical evolution. For 2017. But we have the problem with the study intake for the higher redshift galaxy, because the galaxies are faint and you need the expensive spectroscopy if you want the study in detail. And so you require the large aperture or a space-based infrared telescope like the Webb Space Telescope, or in the future extreme large telescope. In particular, if you need or if you want the study of the physical property, like gas kinematic, require the high resolution spectroscopy. This is more expensive to the photometry, for example, and you need the high signal to noise, even with the James Webb Space Telescope, are extremely challenging. But propose the solution. It's the study in more detail the high redshift galaxy, but using the local analogs to the Lyman-break galaxies. Because some galaxies in the local universe have in the redshift 0.1.3 have the similar property to observe to the Lyman-break galaxy, but the benefit is the accessible observation with telescope to 8 to 10 meter diameters. And in particular, if you want to study the gas kinematics are possible with the high resolution spectroscopy in the optical, we use, for example, BLT with Xshooter spectroscopy, and for example, Lyman-break telescope with pieces. This is the name of this software. They are different to the analog to the high redshift, but our focus is the Lyman-break analogs. These galaxies are at the low redshift between 0.1 to 0.3. They have the low mass, but the particular property is the highest star formation rate. And they are luminous and compact in the ultraviolet light to the Lyman-break galaxy. And another property is this sample showing the morphological variety in high fraction, the object with sign of the merger. This is the BBT diagram of the overseer 29. This black square, it's the sample, and this galaxy is the found is dominated by the star forming and composite. And another property is for Amorim 2010. It's shown this galaxy showing the subsolar metallicity. It's red. But have another Lagrange analogous like to Green Pea galaxy is discovered with Galaxy Zoo project and studied by different authors like Cardamone, Amorim, Isotop Fernandez. And this difference between the Lyman-break analogs to the Green Pea is the how to classify this galaxy. In the LBAs, LBAs, you use the photometry in the match with the galaxy with Sloan, with the need the galaxy are compact and luminous and ultraviolet, but with this galaxy using a spectrophotometry, and it's the using the intense emission line. In particular, this galaxy high equivalent with the oxygen 3 in the range the 200 to 1000 amps. And this galaxy is the subsolar metallicity. And this is the typical spectrum of the Green galaxy or Fernandez et al. 2022. The hypothesis is the study of the emission light profile kinematic with the feeding the Gaussian component. A different author like this is the showing or found the starburst have complex profile kinematics. This is the work for Hogarth 2020, and in general, this light profile have a strong deviation for the single Gaussian. If you want to mark the one Gaussian to the fitting this profile. And we have the narrow component. It's the central and brightest, the profile, and you need another component. It's the broad component. It's reflects in the wings. It's the more turbulence like the narrow component. In this work, using the 14 galaxy with PLT Xshooter spectroscopy, spectroscopy type the long slit with this size, and this data is deep and the high resolution. And we have the large spectral range, but we use only the visual range. We have, you can see the more important lines, and this is the typical spectrum. And where is highlighted the brightest emission line, for example, X beta, oxygen 3, X alpha. This is nitrogen double, nitrogen 2 double, and the double sulfur 2. And this is some galaxy in the phase color HST image for overseer 29. Yeah, the methodology. It's the result for the methodology is we have the data spectroscopy and the accessory base, we have the result image for HSC. And with this data, with the model for the emission line using the Gaussian components. And after we have the kinematic interpretation, and finally with the physical interpretation. The fitting line profile. It's the multi-component Gaussian fitting. It's our previous work. For example, Amorim 2011, Philpott 2010, Bots 2019, and Howard 2020. And for this fitting line profile, we use the line library developed by co-advisor Vidal Fernandez. In this library is based on LMFit. This is an algorithm to provide the fitting, forming the fitting. And LMFit, it's provide the statistical parameter to evaluate the quality to the fit. For example, Chi-square, reduced Chi-square, or Bayesian information criterion. And another point is library, if you allow the additional physical constraints. For example, theoretical flux radar, or you can copy the kinematic for the brightness and another line with the less signal to noise. This is the flux diagram of the methodology. So you need the input during the spectrum one-dimensional and selection of emission line. And after you define the region to fit and establish to the continuum. This is the oxygen green, and it's the shadow green. It's the region of the line to fit. And it's the shadow red. It's the region of the continuum to fit. And after you start with the single component Gaussian fitting, and in this case, you have three parameters like the center, the amplitude, and the sigma. And after you need to have the visual inspection and analyzing of the statistical parameters. For in this case, you can see like one single component. It's the wind. It's not very well modeled because you need to add another component. And in this step, you decide if they add another or not component. In this case, yes, add another component, and you have two options. You can start with 6 free parameters, or you can have constraint to, for example, copy of the kinematic of constraint to the sigma to amplitude, whatever. And in this case, you can see it's the same, so in the same line, it's the winds. It's the very well modeled with 2 components. And another, again, we can visual inspection and analyzing the statistical parameter. It's decide add another component. In this case, no, it's you find the final fit. But with library, give me the observational velocity dispersion. So you need the correct by the instrumental velocity dispersion and the thermal velocity dispersion, and finally you have the intrinsic velocity dispersion. Now, how the example is fitting. For example, start with the compact galaxy. This is the image space color for HSP, and this is the image of the image optical filter. And this in green, it's the side-eye orientation to the slit for the observation. So it's very important to the fit. And we compare example with one component or two components. And this is the value. And for example, for one component, again, you can see the winds. It's not very well modeled. And reduced chi square, it's 7.2. And we add another component like this. You can see it's very well modeled, and the residual it's look better. And another point, it's the reduced chi square. It's better to the one component because in this case we have a reduced chi square 2.7. Now it's another example. It's another compact galaxy, but in this case, for the orientation to the slit observation, you can resolve more than one narrow component, like this. But you see two components, again, the wind is not very well modeled, and add another component, and finally fitting with 3 components per line. And residual is very well. And this part is modeling very well. Another thing is the consistent kinematic for the all line. For example, a recombination line or nitrogen 3, sulfur 2. And this is the case for the extender or interaction galaxy. This is the more complex profile in the sample because finally we fit 4 components per line. Because you can see in the image, this is the interaction and the side and position orientation to the slit. It's fast for these 2 bars. And this is oxygen 3, and this is H alpha with the nitrogen 2. It's the more complex profile because I have the 12 components in the but a question because you think is how to determine this center is the fitting profile. For this, I use the 2 accessories data, for example, the image for HSP and the 2 spectrum data. In this, I have the contour map of H alpha or maybe oxygen 3. And with the contour map, I found the maximum like this or this and the asymmetries. Because you can see how to change this part, and in a specific profile, you can separate to the bars. And using this and this, I determine the position of the center of the Gaussian, because the more important is the have the physical interpretation. This. And the summary, the ionization gas kinematic. Finally, we have model with 2, 3, or 4 components depending on the H galaxy. I have separated to type the component. It's the narrow component with intrinsic velocity dispersion less than 19 kilometers per second. And this component contributing to the majority percentage of the total flux. And this component is consistent with the rotation of this galaxy and associated with the star forming regions. But I have the broad component with intrinsic velocity dispersion more than 90 kilometers per second. And this galaxy showing the turbulent gas and likely associated to an outflow. This result is consistent with the previous work. And this plot showing the compared to the intrinsic velocity dispersion of the H alpha versus intrinsic velocity dispersion to oxygen 3. And this line is the relation 1-to-1. And you can see it's the better relation between these parameters. And now determining the correction for gas extinction. For this, I used the Gaussian law, and we investigate to the difference between the overall component of the H component for the luminosity correction. And this will have the extinction in magnitude, the total, the load, and this is the extinction difference between the global less broad component, or in this case, global less narrow component. And this touches line, it's the case, it's the not have difference, but we found the significant difference between the overall extinction and the H component. For this reason, we use the global extinction as well as the extinction specific to H component for luminosity correction. And now it's the first time they using the relation L sigma for this the type of the galaxy. And this relation describes the virial motion through the gravitational potential of the star-forming galaxy or the young star-forming region. For this study is for Terlevis Melik and 81 and Chavez 40. And it's in the gray scale, it's the galaxy H2 to high rated local and inclusive the young region H2. And it's the blue, it's the sample. And this, you can see the narrow component. It follows the L sigma relation. This is compatible with the H2 galaxy and H2 region, but this means they do not require the additional energy to describe the virial motion. But it's the broad component with the velocity, intrinsic velocity dispersion more than 90 kilometers per second. Do not follow the relation is such the presence of the additional mechanism to the interpret this luminosity and this intrinsic velocity dispersion. And this mechanism, for example, maybe again stellar wind, expansion of supernova remnant. And now we have the BPT diagram. And again, separate with the integral flux and the flux by. We found that most galaxies are dominated mainly by the photoionization for stellar massive star. But I'll draw some following the shock radiance in the integral flux and it is separated by component. In this case, we have more component, it's the fall in the safer regions on the composite. This is because the integral flux is dominate for the narrow component, and this component it's probably dominate for the photoionization of massive star, but maybe galaxy or some galaxy we have contribution with another mechanism, but it is dominated for the photoionization. Now determine the electron density of the component. This is the very important property to characterize the star forming regions. And for this, using the spectry, it's the library the Well-Fernandez et al. Preparation. And for this, you need the sulfur 2 double, the flux, and the temporal electron temperature. For this, using the same sample determined for Agudelo 2023. And after you multi-parameter simulation, 1000 steps, finally result the density distribution, and I determine the median for this distribution. And you can see some example to the fitting to the sulfur 2 with 2 components and the more complex with 4 components. And now it's the outflow characterization from the broader scope. For this, you determine the mass outflow rate. It's the mystery how much mass eject for the outflows, and the mass loading factor. This property which the measure to the efficient to this outflow remove gas to relative to the star formation. Correct. And this assumption and it's followed for another words. And now the result is compared with this property, for example, the evolution of the mass loading factor with respect to the stellar mass, and this compared with another observation works and simulation. I compare in this case the square red, it's our sample, the LBAs, and in red it's the sample, sorry, in black is the sample to LBAs to high rating, and in sky blue it's the McQueen, it's the starburst local with the low metallicity galaxy, and this is the local galaxy with no that extreme with properties. And this in purple is the stack of the observation to the Lyman-break galaxy. And found as the decrease the stellar mass, the mass loading factor increase. This is consistent with this simulation. And this is in good agreement with the Lyman-break galaxy, that is the good. And like the low metallicity starburst or McQueen. But apparent discrepancy with another work like Marasco 23 and Concas for the start Concas 22. And we found the different scatter dispersion of the mass loading factor for the same mass. For example, this will have more the value of the mass loading factor. And this suggests the stellar feedback that is not depends only stellar mass and simulated predictor. And now compare it with another properties. In this, compare it to the density surface transformation rate with the mass loading factor. And in this case, it's on the grain. It's the very way to the Helena, this point. But we found the tension with the Fire 2 simulation because it's and in the case the local dwarf in the Marasco, it's the follow trend, but this show the scatter. In this line with Helena 23, we conclude that star formation rate surface density play a role in the impact of the outflows. Finally, we have comparison with another sample, like another type of the local analysis, like green pea galaxy. And in this case, comparison to the star formation rate surface density versus outflow velocity. And in purple, it's our sample, in green, it's the green pea galaxy. In black, it's the Helena 23 Lyman-break galaxy. And we found the compactness of the galaxy increase, the outflow velocity increases. This trend with the person with the value of the 0.75. 77, and this indicates that more compact galaxies generate the more intensive outflow velocity. And this is compares the outflow velocity versus emission line. It's the misery to the fraction the flow within in the H galaxy, H comparison. And this, we found the emission misery is generally larger for the LBAs, but the green pea galaxy showing larger outflow velocity. And this evidence adds the possible anti-correlation like this. The relative contribution is the flag of the flow component decrease and the outflow velocity increases. But come back the another plot and include the green pea galaxy, but we found that the green pea galaxy have mass loading factor lower than to express for the simulation. This is the square green. And generally, this result it's generally confusion because it's another is in this plot showing the green pea show the more intensive velocity outflow, but we can determine the mass outflow rate. This value it's lower to expect. But this discrepancy to associate with the determination the electron density. In this case, using the electron density, the broad component, but we can see if the change with using the global density, the electron density. And this can see with the point it's have the more value the mass loading factor, and this is the thing. It's the evaluate now because how can determine the electron density? This include, it's very hard, it includes very larger errors. And it's the thing is evaluate determine maybe see again the feeding or how determine the relation between the sulfur and the summary. This work is the first systematic study of the kinematic of the ionization gases LBAs by means of the high spectral resolution optical spectroscopy. We implemented a novel methodology based on our previous experience and the urban tools design. And we investigate the nature of the narrow and broad component using different diagnostic. We investigate the property, the ionization gas outflow in LBAs. And we compare with similar results for the LBAs redshift 2 or another analog such as green P or BCGs. And studying the initial line kinematic of LBAs, it's relevant understanding to the impacting the feedback in the low mass galaxy. Thank you.
Thank you very much. Questions?
Thank you very much. So I had a question about the part where you were showing the slit positions on the three galaxies. So the first one was a compact one, but then the other two had more complex morphologies, right? So the first one, for example, can we go to the first one? That was compact, right? Relatively. And then, so the other two, now I was thinking if you, for example, if you go to the next one, we see a blob under the galaxy, right? So this is, if you model these separately, because your slit is aligned along the thing, along the connecting axis of the two. So if you take these two separate and just do the line fittings, for example, separately, do you think this would decrease the scatter in your final results? Because then you would have 2 points, and then, or the next case that you have the merging, the beautiful merging, yeah, like the one, at the top you see there's one bright part and then there's another part curving at the bottom. If you treat these, what do you think? Have you thought about fitting these separately to get the?
In this case, this exercise we did.
Okay.
For this. We separate the collapsum to the spectrum one-dimensional for this data using the pipeline reduce. And in this pipeline, also, because using the pipeline reduce is you determine the 30 pixel in this line, this or this and this, and collapsing another together. And we can reduce collapsing to the using this part and this
Exactly.
part.
Yes, yes.
Yeah. And using this, it's the separate, for example, it's the more brightness peak with these two components and the less intensive part, it's separated with the two another component.
Okay. And over here, you're only showing the brighter one.
Sorry?
This is only the brighter component.
This is
No,
again.
this is
Or this is the whole.
Yeah, see,
No, this is
yeah,
the
the
whole
to-
thing.
the whole.
Okay.
But she did the exercise
Ah,
of
okay.
extracting
I don't
in the
know.
2D
Yeah,
spectra.
exactly.
You can extract. I think you have the other plot. This one.
Yes.
Yeah, there was.
Yeah. In this plot, each of these crosses you can extract. Well, not each,
Exactly. You can.
but those which are especially resolved. you can extract if you overlap the different profiles of each of this, you will get the whole thing, and you can fit individually. Yes, that's good.
No, I was going to ask the same question, but then I was looking at that. Okay, you have it. I'll ask you.
In this computer, I have the example.
Okay.
1 minute.
Yeah, no problem.
It's the same profile as the Xshooter lines later.
Yes.
This. I compare.
Okay.
It's the one extraction and another,
Yeah.
and it's the whole.
Oh, the green and the red. So
Yeah.
the blue and the red
See,
are
it's
the different
different
components.
extraction.
Okay.
Now
Yeah.
using this and the map contour and
Yeah,
another,
yeah.
I determine the center, the fourth center.
Okay.
Yeah, I was going to ask the same question, but also I think you have it. How does it map the different in the 2D that where the W's, the different crosses, where are they in the image? Where to see where we are looking from. And I think you have it in one of the extra slides.
This are,
No. In one of the ones that you passed,
yeah.
you have the
See, another exercise it's determine the
to see that was
calculate the angular distance and the projected is the image and it's
Yeah, with the distance and the position angle.
and it works, no? Is that
it's the first maximum and another maximum.
So that remind us the upper, so the most distant clamp that you see in the spectrum is the clamp over there.
Yeah, this and this.
wow? I thought it was going to be farther away.
And what's the size of this cutout you're showing in arc seconds? Or
6 seconds.
6 arc seconds.
This is HST.
Yeah,
Yeah.
HST. Yeah.
But you have great resolution in the spatial resolution in the spectrum.
In the
Yeah, exactly.
This is,
Because I thought it was going to be.
No questions?
In fact, I mean, can you see? I don't know if so. That below is the HST contours, no?
Yeah, it's the optical
it's a
picture.
V-band.
This is
R-band.
606.
Oh,
6.
as you can see, that is the farthest away. That the yellow that you're pointing is the brightest. But in between, you can even see, at least in the spectra, you can see that there are some other clamps that maybe they are not even resolved
Yeah.
clearly in HST. But you can see them in the.
Well, this is gas. This is continuous.
So that's a spectral line.
Yeah.
In the,
Yes.
So no,
Yes,
but
of course, of course.
in the imaging, I mean, you have the continuum.
Yes. Yeah. Not that they are too small to be seen, but they are not bright enough in the continuum. to be
Probably
seen.
the gas is connecting the two clamps.
Yes.
I think was the last line.
No. I think it was slit.
Questions?
I have one question. Very nice work. Have you thought to study this with 2D spectroscopy, like have a spatial resolution and also the spectroscopic resolution? So you will have of maybe all the galaxy. Well, it depends on the size of it.
Can you repeat this?
Yeah, if this is study in future work, or you are studying this with a 2-dimensional spectroscopy.
Yeah.
Like spatial resolution and also spectroscopy. You have like a data cube, and if you want to study kinematics, you can be interested like Megara,
Yeah.
or something.
Yeah.
You can study also the is fraction.
That's the work of them.
Yeah. It's another student of the group, the Ricardo, it's using GIMOS for the study the some Green galaxy in the IFO, the spectral and the spectral resolution.
Do they have the spectral resolution? Like what's with, I guess because with all these fittings, you need a good resolution.
GIMOS is not as high as this one. So this is nearly 9,000.
Sí, no
So GIMOS is 5,000
Okay.
in the high version.
It's hard to
Yeah.
found the IFO to the high resolution spectroscopy and the spatial.
For the green teas, which are extremely compact, is tough. This
Yeah.
is very difficult to apply this methodology to identify from which part of the galaxy the group components come from.
Exactly.
Things like that. But perhaps for this sample, it's it easy. We don't have for this sample.
What's the resolution of Megar?
Yes,
But these are probably in the south.
These are
Yeah, this is but no, just
Yeah,
for
but-
reference.
The resolution definitely, I mean, that's
Yes.
20,000.
20,000.
20,000, Megar is 20,000.
Yes.
Oh, okay.
You can get it.
So even with a to binning, you can.
Yeah.
The issue could be,
They use the spatial resolution.
Eh?
The spatial resolution.
That's the problem.
These galaxies
Yeah.
are inside one fiber.
Yeah, it's yeah.
I mean,
Wow.
okay,
The only-
no, the megala fibers
No,
in the IFU is 0.6 hours.
Yeah,
So
this
it's,
is-
yes. You're
Two fibers.
we too much.
And you need exceptional scene.
Yes.
Conditions. And the only attempt that for this sample, the only attempt to do this kind of job with IFUs was in Keck with Osiris, but this is near infrared with adaptive optics. This is work by John Gonsalves in 2010.
Sí.
And the results are quite consistent for a few galaxies that overlap this. So in terms of the dispersion, but with partial lines.
Oh, okay.
Have you compared the properties of these components of the width of the broad component with other properties of the galaxies? Fraction of escaping photons or any other?
Yeah, not for this sample, but
No.
for the green teas,
The green piece.
because this sample doesn't have any line continuum separation.
Okay.
Because they are, they are in the redshift range, which is not so good for which is because observations of the file will be to get the line continuum.
But maybe you can compare that with, for example, the oxygen 3 to the beta ray.
Yeah, sure. That's a good idea.
Because that would be.
You mean with
like a-
indirect diagnostic?
Exactly. Because in the BPTs that you show, some of them fall in the cipher region. Maybe because of shocks or because they are matter valued or something like that. So you could try to correlate the kinematics with the excitation properties. So if for example, if these are shock excited, then I would expect that the larger the width of the broad component, the higher the excitation.
In this plot, the red ones are
It's
the
for
broad components or the narrow?
The red is the broad component and the blue is the narrow component.
But you see that in you still get narrow components which matter.
It's not so clear cut, no? That the broad
Yeah.
component or the narrow component are one thing or the other.
No, it's not very clear. Yeah. But we did this for individual galaxies, right? So some galaxies in the sample might have some feature. Like for instance, the one with the conflict with the stable complex, which has really strong contrast.
Just a small comment for the start where you were showing the Lyman breaks at the different redshifts with the HST throughputs. They look more like the Lyman alpha essentially break, right? Not the Lyman break, right? At the very start. Yeah, this one. Because we have the Lyman alpha line, which is strong, but for the Lyman continuum, essentially the part where we enter the continuum, we don't expect such a strong. So this would be the Lyman alpha break. Yeah. Because I remember my thesis was also on the same and on HST Lyman alpha breaks, Lyman breaks, and then I discovered that it was really frustrating for me that like the papers at that time when they were studying the luminosity function at some redshift, there was the Lyman continuum break. At some redshifts, it was the Lyman alpha break. And then they just generalized the Lyman break. And it was really...
for this redshift Lyman continuum.
Yeah.
I have a question. Maybe this was not your work. By the way, great work. But how was the sample selected? I heard something about UV and compactness, but I don't know.
How selected the sample?
Yes. How was this?
The first or the whole sample to the LBAs is the max to Gallet with León. And this is the goal. It's the same, the compact and luminous with these characteristics.
Okay.
And this sample, the whole sample is the 74 galaxy. And after it's the subsample, if the star for 17 galaxy, but use only 14 galaxy because one is not the observation, it's no good, and two, it's the candidate to AGN. And this sample, because it's the showing the whole property, the initial sample, and the showing the morphological variety and the compact galaxy and the interaction galaxy.
Okay, so that is the selection, no? Like luminous in the UV, isothermal rate, low mass, and that redshift range.
But that's this is the original selection done by Tim Hetman group. So based on galaxy, so just to match the Lyman-break galaxy samples that they have at the time.
Okay.
So it's purely photometric.
Sí.
But her sample is quite representative of the whole LBA sample, just because the Xshooter data was very expensive.
And how different is this from Greenpeace, for example?
In terms of
in what?
In terms of metallicity and mass,
so
you have this
higher masses and more metallic.
The ones with the field squares, red squares, are galaxies which are there are 3 of them which are classified both as Greenpeace and LBAs. I think one of the examples of the compact examples you show is a galaxy that is also included in carbon monoxide from Greenpeace. But you see that there are many others that goes up in mass and metallicity. In terms of ionization and diagnostics, they tend to be lower excitation. Okay.
I'm guessing also that if you're not selecting in emission lines, they probably have lower equivalent widths than the Greenpeace.
The lower
on average, but you may have some of them very strong.
So maybe an older starburst in terms of in mega years, but older because it has UV but less.
Yes.
I don't know. I mean, I'm just guessing.
Yeah, probably yes.
Because that could.
Since you select by UV continuum, it might be you might tend to select longer stuff.
Because that could have also an implication. So when you try to compare with the mass loading factors and the velocities, etc. But that would be the opposite. I would expect, I don't really know, but I would expect faster at the beginning and then.
It depends how you interpret the Bell components. Because if you only ascribe these components to stellar winds, for instance, then of course younger starbursts will have stronger winds. But you have supernovae which come later.
Okay.
So after 10 million years, you have the first generation of massive stars called the supernovae. You have the contribution. And on top of that, if you have mergers, you have more short gas. So at the moment, we don't have the tool to know whether this is due only to winds, supernovae, or well, AGNs. We can say something. Diagnostics. The two galaxies that you don't include in the sample are X-rays.
Yes.
So we didn't want to put our hands on this. on these two galaxies. I'm not selected in X-rays.
Any more questions?
So we should look for these kind of galaxies in our surveys, but we need to match with galaxies.
Okay.
We need to include the UV data to the
Yes, and see the differences between those that have and don't have.
Yeah.
Okay. We found it again.
Okay.
Bueno, pero es cuestión de la práctica.